All right. So last time we talked about recursion as it relates to merge sort. Now let's pull back merge sort. We're going to get rid of the sorting examples and just talk about recursion altogether. We're going to look at recursion in general, look at a few recursive methods, but the focus today is trying to get you to the point where you can write recursive methods. We want you to be able to write a recursive method. Reading through is one thing, but reading through a recursive method, we did that pretty early on in the semester, and we're going to revisit that example. But getting to the point where you can write a recursive method is the next level that we need you to get at. Yeah, Autolab's open source. It was originally created by CMU. We have a fork of it where we've been adding some of our changes. And over the summer, we're thinking of rewriting it from scratch and just redesigning the whole architecture. I don't think CMU has the class sizes we have here. And there are a lot of fundamental design decisions that they made that seem to just not scale to large classes like we have at UB. So the lecture task for today is something that, let me just say, this question's a little broken. I wanted this question to be better. I wanted it to be better. But let me go through it and then I'll explain what I mean by that. So for this, go to your statistics and add statistics object and add one more method, Bayesian average. This is handling that problem of a song with 100 ratings with an average rating of 4.9. We want that to be rated higher than a song with one rating of 5. The average rating is going to tell us that that song with one rating of 5 is a better song than the one with 100 ratings of an average of 4.9. But we know that's wrong. We know, it's possible that that other song is a better song, but there's not enough information to tell. There's just not enough information there. Bayesian average is going to address this for us and make sure that that 100 ratings of average 4.9 is going to be rated higher than that. The way we do this is to add a certain number of fake ratings to that song and then a value for those fake ratings. For our purposes, when we get to the score functions in LT4 and 5 and 6, we're going to use 2 extra ratings of 3. So to each thing that we're rating, we're going to take the actual rating, so like one rating of 5, and then we're going to add in 2 ratings of 3, and we're going to do that to every single thing that we're rating. So we add 2 ratings of 3 and then take the average of those 3 numbers instead of the average of just the 5. And same with the 100 with an average of 4.9. We're going to add 2 ratings of 3. Now the song with one rating of 5, that's really going to take a hit from those 2 3s. That's really going to affect it because we have a lot of uncertainty. It's kind of measuring that uncertainty. One person rated this. We just don't know. We're going to pull it closer to 3 with these 2 extra ratings. But the song with 100 ratings, that one isn't going to be affected by those 2 extra ratings hardly at all. So now that song is still going to have an average close to 4.9, while the song with an average of 5 took a hit from those 2 extra ratings of 3. So it evens out the kind of the playing field and rewards songs with lots of ratings by not affecting their rating too much. But songs with very few or even just 1 rating, those are going to be affected and pulled closer to 3, closer to the middle rating, an average rating. To do this, we're going to use the same setup we've seen. I'm going to hit you with this first order function over and over and over again. So those of you trying to figure out how that average works with that function that takes a t and returns a double, you got to actually learn that because the first 4 methods that I'm asking you to write for this project all use that same setup. Bayesian average is no different. Type parameter t, a list of type t, and a function of type t to double. We're using that same setup. So we have a list of t, but we don't know what t is. It's going to be different. It could be different every time this method is called. So we take that list of t that we don't know how to work with. We take this function, which takes a type t and returns a double, and apply this function to every element of the list. So we're going to take each element of this list, call this function on each element, and that's going to give us a double for every single t in that list. Now with these doubles, we know how to work with doubles. They're just numbers, and we can do our math or our arithmetic we can add these two ratings. We can add these extra ratings to that list of doubles that we have, and then compute the average, and compute this that way. The reason this question's broken, and this is one of those, for your own sake, try to do this the way I intended. I intended this to be a recursive solution where you had to use recursion to find the answer. You would use recursion to add these extra ratings to the list of doubles, and then at the base case of the recursion, compute the average of that list. That was my intention. When I wrote this question, I was all happy, like, this is a great recursive question. And then the very first student who came to me in office hours had a solution for this that didn't use recursion, and as soon as I saw it, I just hit myself. I'm like, obviously you don't have to use recursion here. You just do the math, and there's no recursion needed. I highly advise, so LT4, that in chat some students were having trouble with, LT4 is a tough recursive question. It's difficult. LT3 was meant to be the easy recursive question that gives you a little practice writing a recursive method, so you're prepared for LT4. If you don't use recursion on LT3, if you use the cheese and just do the math without using recursion, you're going to hit a wall on LT4, because this is what was designed to prepare you for LT4. So I highly encourage you to not use the cheese and write this in a recursive way. Write this recursively and write this method that way. Get the practice writing recursion on this method. Usually I have things designed to force you to do the thing that I'm getting you to learn. I missed the mark on this one, but if you take the cheese and don't use recursion here, LT4 is going to be very difficult for you, because you're going to have to learn all of recursion on the hard recursion question. You don't want to do that to yourself. If you're having trouble with LT4, and especially if you come to me in office hours having trouble with LT4, my first question for you is going to be, show me your LT3 solution. If you didn't use recursion there, cut it out. Use recursion there, because I told you this in lecture. A little broken. I'll have to fix it. I'll have to fix it for next semester, but this semester, it is what it is. We have a cheesable recursive question. And even if you get through if you get through LT4, you're good. But AO1 is a huge recursive question. You have to write that using recursion as well. So if you don't have the practice, it's going to be tough getting in there. Okay. And I don't see a way how you can cheese LT4. I believe you do have to use recursion for LT4. I don't think you're getting away with that. But this one, since it's all arithmetic, you can just write an equation that computes this for you, or use the resources that I gave you. This is why I'm really kicking myself. Just use the resources that I linked to in the documents that I gave you, which give you the equation. But LT4, I believe LT4 you have to use recursion. I can't fathom a way to do it without recursion. Maybe. No, that'd be maybe, but you'd have to really use you'd have to have some fancy usage of the data structure methods like we saw on last Wednesday. You'd have to get really tricky with those things. That's probably doable, but way harder than writing the recursion. Okay, so let's revisit this recursive example. We actually looked at this example when we first looked at stack frames, and we analyzed what was happening on the stack. Challenge accepted. I'd love to see it. If you can do LT4 without recursion, I think it might be possible, but very, very tricky. Very tricky. Learn recursion on the hard question, then you'll have a better understanding. It's not how education works, though. You should have a nice, you should be eased into each topic. Don't just jump into the hard one. But hey, if that's what you believe, Priest, just jump right into AO1. Have that be the first recursive method you write. All right, so let's take a look at this. A nice, easy intro into recursion. We've seen this when we were talking about stack frames, and we looked at the stack frames that are added to the stack as we go through the recursive calls. Today, I want to focus on how you would write this solution. If I gave you a question that said, compute the geometric sum of a value n, starting with n and going down to 1, the sum of the values n to 1. I'm looking at this now and I'm realizing that's not what geometric sum is. Geometric sum would be fractions. I've used this slide like 3 semesters. I just realized that this isn't geometric sum. And nobody's called me out on that. That's amazing, actually. All right, but we want to take the sum of numbers from 1 to n. And you can't use var. If that were my lecture question for you, that was the task that I was putting out to you. How would you arrive at this solution? Arithmetic sum? Geometric sum, I believe it's the sum of fractions, 1 over n. Or is it 1 over 2 to the n? I forget. But this ain't geometric sum. So let's take a look at this. On input 3, this should compute 3 plus 2 plus 1 equals 6. Let's talk about it. So what I recommend 4 ingredients to successful recursion. So let's go through those ingredients and see how each of them are applied in this method. The base case, which is a trivial input-output behavior. The recursive step, which is going to make a recursive call, which we're going to write under the assumption that our recursive calls are going to be correct. Yeah, technically it's the sum from 0 to n in my code. The recursive call, which we're going to write under the assumption that our recursive call is correct. We're going to make sure that our recursive calls get closer to the base case. And some 4th ingredient, which I'm blanking on right now. All right, so I think it's related to one of the other 2. I think I said it in there. But the slides will correct me if I'm wrong. So the base case, this is a trivial input-output behavior. So if I'm computing the sum of values from 0 to n, what's a trivial base case that I can think of? And the order in which you follow these steps can vary. It's up to you. It's up to your preference. On Friday, I started with the recursive step when we went through merge sort. Today, I'm starting with the base case. Whatever way helps you think about this the most, you can follow. Today, I'm going to start with the base case. So the base case, if I'm computing the sum of values from 0 to n, what's a trivial input-output? You can choose some input where you just know the output. I'm going to choose 0 if n equals 0. And I'm going to handle negative numbers here because they don't make sense. I'm just going to say a negative input, we're just going to give you 0. But if you give me 0, the sum of values from 0 to 0 is 0. I can do that math. Trivial input-output behavior. We could also have this be 1. If we could say n less than equal to 1, just return n and maybe decide how we're going to handle negatives. But you get the idea. The base case is always going to be some trivial input-output behavior. And your method's going to start with a conditional. We're going to say if we've reached the base case, just return the trivial output to this trivial input. Rough day for Jesse. I'm just being a little more honest today. Usually I just don't say those things out loud. I would notice that and just be like, maybe no one else will notice. I'm just being open today. So the trivial input-output behavior, and we check. Are we in the base case? If so, just return the answer. We know what the answer is. If we're not in the base case, we're going to write our recursive case or recursive step. I usually call it recursive step. If you want to call it the recursive case, that's fine too. But the recursive step is going to be an amount of logic. Oh, I know what the 2 are. That if you're not in the base case, do the recursive step, and then write the recursive step based on the assumption. Assume that your recursive calls are correct, and then write your logic with that assumption, and then make sure you get closer to the base case. I was just combining 2 of those into one, and I combined them on the slide too. So we're going to write this recursive step. Somewhere in here, we're going to make a recursive call. We're going to make a recursive call to the method itself. Recursion, the definition really just means you have a method or a function that calls itself. We call that the recursive call. So when we make somewhere in here, we're going to make a recursive call. If we don't make a recursive call, that's another base case. That's one of our base cases. The base cases don't make recursive calls. So somewhere in this recursive step, we're going to make a recursive call. We're going to call the method that is currently being called, which seems like magic, and we're going to pretend that it is magic. Whenever we make a recursive call, what we're going to do is just assume that it's correct. We're just going to assume, Jesse on the slides, 3 minus 2 is 1. Jesse on the homework, write me AI. That's actually quite accurate, quite true in all of computer science. We teach you the tools in lecture, and then for the assignments, we ask you to apply those tools. There's a reason why pretty much every computer science course is going to feel like that, which I'd be happy to talk about after lecture. I can give my thoughts on that. So we're going to just assume that the recursive call is correct, and then write all of our logic based on that assumption. I put it as 2 separate steps in Friday's lecture. 2 ingredients to my successful recursion. So I'm going to compute the geometric sum, in this case of n minus 1, because I'm going to make our 4th ingredient, I'm going to make recursive calls that always get closer to the base case. This is critical. As long as my recursive call gets closer to the base case, I'm going to eventually reach the base case, and eventually my assumption is going to be correct. And if my assumption is correct that this returns the right output, and all my logic is correct, I'm going to assume that this returns the correct output. If this computes the sum of 0 to n minus 1, well, if I have the sum of all the values 0 to n minus 1, and my task is to compute the sum of values from 0 to n, well, I'm just going to add n to that, and then I'm done. So I just have to think of the one step that I need to be able to turn this call, recursive call that gets closer to the base case, into the complete solution, which is if this is correctly the geometric sum of n minus 1, guess what I got to add to that to get the geometric sum of n, or the sum from 0 to n? I'm just going to add n to it and return that. So my logic is sound under the assumption that this call is going to return the correct value. And the key to that is always getting closer to the base case. So if my input is n, my base case is any n, 0 or negative, and my recursive call subtracts 1 from n, I'm getting closer to my base case. And eventually, I'm going to make a recursive call that hits the base case. When I make a recursive call that reaches the base case, my assumption is trivially correct. Compute geometric sum of 0. That call is going to hit the base case, return 0, and my assumption is true. This did, in fact, return the correct value. Compute geometric sum of 0, gave me the right answer. 0 plus 0 is 0. Not to emphasize your point even more, Jesse in lecture, 0 plus 0 is 0. Jesse on the homework, write a genetic algorithm that can train a neural network. Yeah, it's a bit different. But this recursive call is going to be correct once it hits the base case, and then our recursive steps can all start returning. Well, 0 plus 1, that's going to return the correct value. 1 plus 2, that's going to return the correct value. 3 plus 3, well, that's going to return the correct value. And we're going to keep returning the correct value all the way up, as long as we reach our base case. How does recursion look in a for loop? You would usually use either a for loop or a recursion, but you can actually, my second example today, we are going to see recursion inside of a for loop. We will get a little tricky, but usually you don't see it inside of a for loop. I won't give you an assignment that asks you to do that. So let's take a look at this on the stack. Let's bring up another stack visualization. This is a flashback to when we did this with this exact method earlier in the semester and talked about stack. But of course, now we want to focus on the recursion part. So when we get to this point in the recursion, you should know how we get to this point in the stack. We have the main method, which has its own stack frame, which has a stack frame. We make a method call. The input is 3 for the first call. And we have a function pointer. I'm going to track where the function pointer is, which is the line of code where the function is currently waiting for the next stack frame to return. Something I didn't visualize last time, but now we'll have all these frames on the stack, and we want to see where they're waiting. Of course, they're all going to be waiting on line 5 anyway. So we get to this line in the first stack frame. That gets to line 5, creates another stack frame with an input of 2. That gets to line 5, creates another stack frame with an input of 1. And then that gets to line 5 and creates another stack frame with the input of 0. So by the time we reach our base case, which we're always going to reach because we make sure we're very careful to write recursive calls that always get closer to the base case, since that is the case, then when we call this recursive method, we're going to keep putting frames on the stack until we eventually reach the base case. If it were n equals 0, equals 0, it would still work. It just wouldn't work on negative inputs. I just want to make sure that if somebody gives this method -1, that it doesn't crash. Is the only reason I did less than or equal to 1, or less than or equal to 0. It would still work. My whole example would still be valid if we did n equals 0. It'd be fine. Just, something inside of me says, I don't want to put code out. I don't want to write code that could crash as soon as somebody puts a negative sign somewhere. I just don't want it to break. So eventually we get to a stack frame that has the base case. It's going to start running at line 1, has the input parameter, gets to line 2. This is now true, and we're going to hit our base case, which is our return value. It's the last thing that's evaluated. We go right to the closing braces after that. So this stack frame is going to return 0. And we finally get to a point where we're not adding more frames to the stack. We're not making more recursive calls. Now, instead of making recursive calls and expanding the stack, we're going to start returning and start destroying these stack frames and going back up to this recursion. So we're going to return 0 and give that back to this method that's been waiting. Now, this method, this stack frame, had an input of 1, and it made a recursive call under the assumption that it's going to get the correct value. Well, that was just the base case, so go us. We returned 0. That is correct. We're going to take 0 plus 1 and return 1 from this stack frame. This stack frame returns 1. Now this stack frame, which had an input of 2 and had logic that just said, well, if assuming that you give me the sum from 0 to 1, I'm going to add 2 to that and return that. Our assumption was correct here. That recursive call did in fact return 1, which is the sum of 0 and 1. So we got our correct value. We're going to add 2 to that. We get a return value of 1. We're going to add 2. That's the value of n on this stack frame. And notice we have many values of n, variables named n on the stack. In different stack frames though. All different scope. We're going to add 2 to 1 and return 3. Now this stack frame is going to get the return value 3 from this frame. This stack frame now gets a little more complex. It gets a little more magical, but now you can see where the magic's coming from. This had an input of 3. N is 3. And we're going to say, look, if you give me the sum of 0 to 2, I'm going to add 3 to that and return it. Well, our assumption was correct. We just went through the stack frame and saw that this method call is in fact going to return 3. So cool, our recursive call actually did end up returning the correct value. So that did return 3. We're going to add 3 to it and return 6. If we had another recursive call waiting for that value of 6 that said compute geometric sum of 3, and I'm going to add 4 to it, well, that would work too. We would have that method returning 10. Then something calling that method, the assumption would still be correct. Like, the assumption is always correct as long as we design everything properly. We have to have a base case with some trivial input-output behavior, a recursive step which assumes any recursive calls are going to return the correct value, write all of our logic under that assumption, and make sure that if the recursive call does in fact return the correct value, that our logic is going to return the correct value for our overall input. And the recursive calls always get closer to the base case than the original input. But those 4 ingredients, we have all those, we put them all in this method, mix them together, we get a successful recursive method that does in fact return what we expect it to return. Where's the else block? It's right here. Oh, where's the else block in my stack? I shorthanded that a bit. Since I don't declare any variables in my else, I kind of get away with it. But yeah, there would be an else block in there on the stack. I would get points off for that. Lab quizzes get a recovery plan, yeah. And I should have those out tomorrow. I'll get recovery plans out with all the details and scheduling stuff. The quizzes on, I'll probably do the same thing for LO2. For the quizzes for LO1, I did as oral quizzes, so they were interviews where I pulled up some code, I shared my screen with some code on it, then I asked you questions about the code. See if you can read the code there. So they're much shorter. I do them in 10 minutes. So I just give you one simpler question and just ask you and try to figure out if you can read that code. There are some students who fail the quiz twice because of the reading and typing. So I want to do something a little different. Plus it's easier to schedule and just easier on all of us. Can you teach us how to write the codes for stack and heap for the lab quiz? I'm not sure what you mean by that. Ebro. How to write the codes for stack and heap. Yeah, besides the second chance. Any other questions? Any questions on this example? Yeah, project will be an extension. And all lab submissions are still open. It's actually I had to double check something on that. Yeah. Auto lab submissions are still open. I turned off the application objective grader, that portion of the grader, but it still will grade your learning objectives, your lecture tasks. You should still be submitting those. You can rely on an extension if you're still working on lecture tasks. Application objectives are over. Lecture tasks, you're going to get an extension. I'll have those out by Tuesday. So right now, submissions are open until Tuesday. Then once I get recovery plans out and I decide what the extended deadlines are going to be, then I'll extend it even further. So for the right part of the lab, is it going to be written or oral? I pretty clearly just explained it's going to be oral. All right, no questions on this? Let's move on to anagrams. So this example really is my response to that comment earlier. Jesse in lecture, 1 + 2 = 3. Jesse in lecture in the homework, write genetic algorithm. This is kind of my answer to that. I want to make sure I get a more complex example. Again, this is another example that we've seen earlier in the semester. Let me get the code up there. This is an example we've seen earlier in the semester. It's a little bit slightly different. I did this live coding. I coded it right in front of you last time. So this is a little bit different than what I ended up producing that day, but not really. The only thing different is I used flattened and distinct here because we know more first order functions. We know more methods that we can call on data structures, and I want to show them off. I guess I never showed off flatten. Maybe that should go in that lecture from last Wednesday. But I want to revisit this because you're at a point where you can read all this. Last time I used this to motivate testing. I said, here's some code that you have no chance of understanding. How do you know it's correct? Well, we're going to write unit tests and then know that it's correct. So looking at code, you can't always figure out if that code is correct. You can't just stare at this code and decide if it's correct or not. Even being able to read functional programming, you'd really have to stare at this for a long time before you convince yourself that this is correct. But you write unit tests for it, and then you know your code is correct. Because your unit tests, you're going to compute the inputs and outputs by hand. You're going to know that your testing is correct, which sometimes we write bad tests. Sometimes, I do too. I have to fix my tests because my tests were the problem. That is something I should comment. I meant to go through the examples repo over the break and comment all my code. I did not quite get to it. But now we're at a point where you can read this code. For this example, it doesn't matter if I comment it because it's an exercise on you reading this code. If I comment it, you don't have to read the code. So let's take a look at this and see how recursion was applied here. Yeah, and I'm sure none of you comment. Maybe one of you comments your code. But I should when I'm using code for the examples. I don't know about should, but it's debatable. In this case, no, I shouldn't. Because you know what the code does. What am I going to comment? It computes the anagrams. It's an exercise in reading code. Anyway, let's talk about how recursion was applied and how the recursion is set up with those 4 ingredients to give us a successful recursive algorithm. So, and this isn't true anymore. I shuffled the lectures around, so the lecture that I'm referring to in this bullet point was actually last Wednesday's lecture. You're at a point where you can read all of this. So let's take a look at our ingredients. First, the base case, trivial input-output behavior. And just a reminder of anagrams, we have some input string, and we want to return a list of strings, which is every reordering of the characters of the input string. So when the input string, for example, was Fox, when the input string is Fox, we expect the outputs being every ordering of those 3 letters. And we don't want to have duplicates in our output list. So when we have like double letters here, 2 Fs, we only have 3 possible outputs. When we have only double letters, or if we had this would be the only, it is itself its only anagram. So that's what we want to build. And this method, in fact, does this. It passes all those tests. And we could write more tests. Of course, we can write tests to our heart's content. But we want to make sure we hit at least the edge cases. An empty list. Oops, this does not handle empty list. What did I... It must handle empty list. You must handle it in the recursive step. Yeah, because this would return the empty list. Well, I accidentally handled the recursive step. Hey, that's an advantage of testing, because I have a test case for empty list and it passes. So, but we have a base case. I should have a base case of length 0. Could actually be my only base case, but I need some trivial input-output behavior. I chose a list of length 1. Again, I should have input if input.length equals 0 as well, or just the length 0. That would actually be fine. And then have a trivial output behavior. So the output on a list of length 1, a string of length 1, well, a string of length 1 is itself its only anagram. Just return a list containing that input. It is its only anagram. There are no other anagrams. No computation to be done. Trivial input-output behavior. That's our base case. That we can all compute. We're all good with that. Now we're going to write our recursive step Oh yeah, sorry. This is, notice in here, this is the only time where we actually create a brand new list, by the way. And then as we return up the recursion, we're going to take that list and add more values to it. Create new lists with more values in them. That's the only time we create a list. This is often how it works with recursion, where in your base case, that's where you're initializing values. Like if you were to write a recursive method that computes the sum of a bunch of values, in your base case, that's where you would say return 0. And then as you return up your base case, that's where you're adding. And that's in fact what we did in the last example. We return 0. That's where we're initializing our first value. Like that's where we're starting with 0. And then as we return up the recursion, that's where we're adding +1, +2, +3, +4 if the input was 4, and so on. So once we hit the base case, that's kind of where the logic starts. And then as we start returning from the base case, that's where all of our logic is applied. In some cases, some cases that's not how you're going to write it. But the base case, trivial input-output behavior. Recursive step, we're going to assume that our recursive calls are correct. So we're just going to assume that we have a method named Anagrams, which is in fact this very method. We're just going to assume that it already works. And then we're going to write all of our logic based on that assumption. And here's where we want to read. And here's where we want to read through all of this code and make sure that our logic follows. So our recursive step, our recursive call is just assumed to be true. So if we call anagrams of new string, we're going to assume that that just computes the anagrams of new string. And then we're going to write our logic to make sure that every recursive call gets closer to the base case. So whatever input is, again, I should have my check to make sure input length, check if input.length equals 0. But we're going to take an input of length greater than 1, and we're going to subtract 1 from its length. We're going to do that by taking a character out of that string, which is going to make its length, its original length minus 1. The second lab results haven't been posted yet. Blitzkrieg. By today, it looks like we'll have those out. And then we're gonna remove a character from the string, and that's going to give us an input of the original length minus 1, which, as long as the input length is greater than 1, we're getting closer to our base case. So we're getting closer to our base case. We're assuming that the recursive call is correct. And since it's getting closer to our base case, it will eventually be correct. Once the input length is 1, it will return the correct value. We know that. We have some kind of a seed to get started. We have something to grab onto. The base case, it will return the correct value. Now we just have to make sure that our logic is correct. We have to look at the logic of this and make sure that all this makes sense. So let's look at our logic and make sure. I think this is the last slide I want to talk about. And then the rest, I kind of introduced these functional methods. But we've already seen them, so you don't need maybe a quick refresher on those. But I'll just talk about them through this slide. So we have to make sure our logic is correct. So what are we actually doing here? What we're doing is taking each character, we're iterating over the characters of this string, of the input string. And for each character, we're going to remove that character. We're going to use substring to remove a character. That gives us a new string with that character removed. We're going to make our recursive call on that string with the character removed. And then for each value that this returns, we're going to add that character to the end of that list. That's going to give us a list of strings, where each list of strings are the anagrams of one of the new strings with one of the characters removed, with that character added back to the end of the output for each one of those. We're going to call flatten. This is one that I didn't explain before in Wednesday's lecture. Flatten is going to take a two-dimensional data structure, or a list of lists in our case, and flatten it down to a single list. So it's going to take all of the elements of all of the inner lists and create one list with all of those elements in it. Then I'm going to call distinct, which we did see, which is going to remove all the duplicates for me. So if I do this for each character, so for example, the input is, if the input's at, this loop is going to end up making two recursive calls. One with the a removed, which is going to return all, which new string would be just t, and it's going to return all the anagrams of t, which is just t itself. And then we're going to append a to the end of that. We're going to add the a back in to all of the anagrams, which is just the string t. And then we're going to hit the next iteration of this loop, remove the t, make a recursive call with a, which will return just a, and then add the t to the end of that. So we'll end up with the anagrams at and ta with that input. We're going to use the yield keyword. I guess I will use these slides. We're going to use the yield keyword to collect all the results. So for each character that we remove and compute all the anagrams of, we're going to collect all those into a data structure. This is going to return a list, and we're going to map that list by calling this function, which appends that character to the end of each string in this list that's returned from anagrams from the recursive call. So this is a list. This is the last expression to be evaluated in the body of this loop. I'm using yield, so that's going to collect all of these into a data structure, all these lists into a data structure, and then I'm going to wrap that in parentheses, this entire thing, and call toList on it, so I make sure that that data structure is a list. So I'll get a list of lists where these lists are these lists right here that are created from the recursive calls. Flatten that, remove duplicates, and we got all our anagrams. Ooh, I should have removed those. What does flatten do again? It converts a list of lists into a single list. So let me answer that question in a different way. Let me make sure we got an interesting input here. Okay, so our initial, so let's take a look at this in the debugger and take a look at what's going on in an actual call of this. So here we have the test case off, and we expect the output list to contain off, fof, and fo. So that's our input on this stack frame, and we can look at our call stack. We have some anonymous functions in here. We have some stuff going on, but if you just click the non-grayed out values, that's going to take you to our stack frames. So we can see the stack frames on the stack. We have our anonymous function call. We have our recursive call, and so on. Let's take a look at this until we get to the base case. So we can see we started with an input of off. We removed the O and made a recursive call with just FF. That's going to remove the first F and make a recursive call with just F. That's going to hit our base case and just return the list F. And let's start stepping through at this point. So we return the list F. And we're back to our input of FF. It's going to remove the second F, make another recursive call. Oops, I clicked the wrong thing. Going to make another recursive call with just the list F, hit our base case. We should be at a point where we have a list of lists containing FF and FF. I guess that's kind of hard to see in the debugger because this is such dense code. But we have a list of lists where each inner list has just the element FF. Then we're going to flatten that and call distinct, which is going to return just a list with FF. Let's get to that return. And now we can see we got the first return call from the input of OFF. We removed the O, made a recursive call of FF. And now we're going to go through our map method, which is going to return the list FF, but with the O appended to the end of it. So map takes a function, calls that function on each element of the data structure, and returns a new data structure with the outputs of this function. So this anagrams of new string returned a list that contained the value FF. Our I here is 0, and our input is OFF. So input char at 0 is going to be O. So it's going to take that list that only has one element in it, FF, and append O to the end of it. And then return a list containing the value FFO. Very, very useful. And we talked about that if you want more details. We talked about that last Wednesday. So we're going to keep going through that loop. By the way, whenever you get into code that's not yours, click this step out button, and that's going to take you back to your code. We hit the base case with F. Let's keep stepping through until we get to a good place. So here we're back in the top level call OFF, but I is 2, so we removed this second F. So we're almost at the end of this call. We removed this second F. New string is OF. And we're almost at this part. So the input was OFF. This is after all the recursive calls. So after all the recursive calls, we ended up with these lists. First, we removed the O, made 2 recursive calls on FF and hit the base cases, got a list of FF, appended O to the end of it, and got FFO. That was the first one that we just went through. Then we removed this second F. This is when I was 1. We removed the second, or the second character, but the first F. We removed the first F. Made a recursive call on OF. That was new string. That ended up giving us OF and FO as our return values. And for each of those, we're going to append that F that we removed to the end of it. Then the next recursive call, we remove the second F, really the same kind of logic. We have a recursive call for OF. It's going to return the list FO and OF, then append F to the end of each one of those. Then we're going to call flatten, which is going to collect all the elements of each of these lists. So this is a list of lists, and we're going to take all the elements of each list and combine them into a single list, and then call distinct, which is going to return a new list with all the duplicates removed. So FOF, OFF are both in here twice. This list already had its duplicate removed through a recursive call that called distinct, but we're going to remove these duplicates and just return a list. And just return the list X, and return the list OFF, FOF, FFO. Then we go to our next test case, and we go through the next one. Next test case is just A. Not interesting. Oops. Oh, we're on CSE. And they were in the middle of an input of CSE. And you can see the same thing. CSE made a call with just SE with the C removed, made a recursive call with just which will make a recursive call with just E, if we can get there. Trying to get to a nice stopping point here. CSE made a recursive call to SE. That got the return values of ES and SE. And then we go to the next recursive call in the top level call. Now we're going to remove the S and make a recursive call for CE. That's going to make a recursive call for just E and just C. And we're going to keep iterating, keep making recursive calls until we get all of our return values and then collect them all into our return value.